Okay, thank you so much, and good afternoon, everyone. I hope you guys had a good lunch and have been enjoying sessions since morning. So maybe a brief introduction of myself. So I'm Gaurav. I'm the solutions engineer from Google Cloud. I've been working for Indonesian customers for almost 2 years now. I'm like the first technical point of contact for Google Cloud for majority of customers in Indonesia, and like I've been working with Gojek, Traveloka, Tokopedia, Salestalk, and many more. Okay, so what we're going to discuss today is pretty much in line with what Imre spoke in the previous session. So basically, Imre did a very good job in giving a complete overview, right from data ingestion, preparation, visualization. So I would be mostly focusing on streaming analytics, which is kind of very popular these days, and majority of digital native and e-commerce companies have been doing a lot of streaming analytics. So before we actually jump into streaming analytics, let's kind of understand what streaming means in itself. Okay, so data can be big. It can be like very big. So when I say big, very big, it can be in range of terabytes, petabytes. I still remember like 10 years back, the biggest data which we used to call is like 1 terabyte. That's already gone now. So apart from the fixed batch size data, what we have these days is the streaming data, right? So as people use applications, they use platform, data keeps getting generated and gets into the system. Now, if you see this, basically this shows a stream of events coming from an application, for a particular duration of time. So you can see like the ones in different colors, they are basically the events coming from different kind of interactions from different functionalities within the application. So one of the biggest challenges with stream is delay or late data. Let's say you are playing a mobile game and you're sitting in a flight, and your flight is like for 10 hours or even 12 hours. So whatever activity you do while playing the game, that data would only get pushed into the system once you get a network, right? So if you see this example, you can see that there is data which got generated around 8 a.m. and it showed up almost around 8 a.m. There is another one which is highlighted in yellow, which also got generated at 8 a.m. but showed in the system slightly delayed. And there is the one which you see on the corner, the green one, that data was also generated around 8 a.m. but it came into the system only around 2 p.m. right? Now let's say if I'm building an analytics on top of a stream, and if I don't handle late data, then probably I'm going to have a lot of issues in my analytical computation, especially when you're dealing with transactional data. So imagine you have a POS system, and that POS system keeps sending transactional events every second or every half a second, right? And if the one of the transactions shows up very late, and you exclude that from your computation, then your overall final dashboard or final analytics might show some erratic numbers, right? So that's why it's very important to handle late data. Now, when we are talking about a stream, there are various use cases and various ways in which you can process a stream. This is basically element-wise transform. So basically you have multiple events coming in, and each and every event has different attributes. For example, let's say we take the same mobile game example, and I just want to filter out a certain amount of users from a particular region. So in that case, I won't worry about the processing time or ingestion time. I'll just filter, in this case, let's say the yellow records, right? The yellow events. So this is okay. The problem starts coming in when we have to group data in processing time windows. Now, let's say if we are talking about batch data, so if we are doing our analytics on top of batch data, and we are doing that in some specific time intervals, we already know that by a particular time, the data is already there, right? So in that case, we can use processing time windows. But if we want to build our analytics based on event timestamp, now, if you take the same example, an event which was fired up at 8 a.m. appeared in the system around 2 p.m. Right? Now, if you try to group that event across different time slices, that event might show up in a different time slice if you are processing using the system time or the processing time. But if you are using the event timestamp, even though that event shows up at 2 p.m., but still it would fall into the first bracket, or the time frame in which you are trying to process, which might be, let's say, 8 to 9 or 8 to 10. Okay, so that's like so that was like batch windows. We have another concept which is called, so that was the fixed windows. We also have something which is called as sliding windows. Now, let's say if you want to build if you want to do analytics, let's say between 8:01 to 9:01, 9 and 8:02 to 9:02, there might be some events which might get overlapped. So basically, you just slide the time, by 5 minutes, 30 minutes, or 1 hour, and then you generate your computation. There is also a concept of data-dependent window, and this is what makes Apache Beam very unique. For example, let's say you have an application and there are multiple products and services in that application. And as a user, I start using one of the services, and within the same session, I also use multiple services within the same application. So basically, using the session window, you can actually group a particular user's activity into one single slice. So let's say if I take example of a flight booking system, an OTA basically. So I booked flight, I booked hotel, I also purchased some event tickets. So basically I did like 3 different activities within one single session. So we can use the user ID, or we can use the session ID, and we can basically find out what that user has been doing in that particular session. And that is what is called as session-based windows. So we talked about windows. So by windows, we actually know where the events are being generated, in the stream. But the question arises when to process them, because in a stream, you never know when the data is complete, because stream is continuous, right? So there has to be, you have to define when you want to process that data. Okay, so if you see this graph, so the first one, so we are using the same mobile game example. So if you see an event which was generated around 12, showed up around 12, and there is an event which was generated at 12:01 which showed up around 12:09. That's the number 9, right? Now we have a concept of watermark. So what's watermark? It's basically system's estimate of when data is complete. So with the Apache Beam SDK, the watermark concept basically predicts that when the data will be complete. So basically, as your data is getting streamed in, it looks into the streaming buffer and it predicts when the data is complete. Now, if you're doing a batch processing, which is like you're processing at the end of the day, you don't worry, because according to system's estimate, by end of the day, the data is already there. But let's say if you're processing every 1 minute, so in that 1 minute, there might be some data which might come late, which is that number 9. So if I'm trying to do an aggregation between 12 or 12:02, even though that event 9 was generated at 12:01, I will miss that event because that came in late. So how does Apache Beam handles this late data processing? So in Apache Beam, there is a concept of accumulation and fired pane. So basically, you can define that whenever the late data comes in, you can take a decision. That is, either you add that data to the existing computation, or you just discard the previous data, or add and just take the new data. So in this case, when we did an aggregation before between 12 to 1202, the sum was 5, right? Because the event 9 appeared at a very later stage. So with using the accumulator pattern in Apache Beam, when the event 9 comes into the system, basically it will automatically get added to the previous computation. So you'll get the sum 14, and you wouldn't have to reprocess that event 9 separately. So that's where the Apache Beam SDK becomes very useful in handling the late data. Traditionally, what people have done handling late data is that as you keep processing the data which comes in, and the late data you store it separately, and then you have a separate process which kicks in, and it basically takes that late data and then merges with the existing data. So using the Apache Beam SDK, you don't have to do that. You just have to define what you want to do when the late data comes in. And the SDK supports that out of the box. Okay, so basically what Apache Beam brings to the table is it is a SDK using which you can do both batch and stream processing. So traditionally, people have been using Hadoop, Spark, and other open source technologies to do batch processing. And then if you have to do stream processing, you use Spark, Flink, and there are other open source frameworks as well. With Apache Beam, you write one code, and using that same code, you can do both batch and stream processing. So overall, your team doesn't have to learn multiple, frameworks or multiple technologies to do the same thing. It was open sourced by Google, early last year, and whatever code you build on Apache Beam, there are various ways in which you can run that. So on Google Cloud, we have Cloud Dataflow, which is the service which is the fully managed service on top of which you can run your Apache Beam pipeline. If you are having a Spark or Flink or even an Apache Beer Pump environment, you can run the same code there as well. But the benefit of running your Apache Beam pipelines on Dataflow is that you don't have to secure or pre-build infrastructure beforehand. So as your data comes in, your pipeline kicks in, and it automatically generates servers on the backend, does your processing, and throws the server back. Traditionally, if you're using Hadoop or Spark clusters, then you will have one single fat cluster up and running 24/7, and that's most of wasting resources. So with Cloud Dataflow, even though your data volume increases, it just increases the number of servers, and it just throws down those servers when the processing is done. This is a very simple example of how the processing happens, in using Cloud Dataflow. So the first step of a pipeline is always to read from a source. Since we are talking about streaming, so we have, and in this case we are using PubSub, which is the messaging bus in Google Cloud Platform. If you are aware of Kafka, MQTT, PubSub is also a fully managed, messaging service in GCP. So the first step is always to read from a source. If you're reading from a bounded source, then it would be using the other connectors, other IOs. In this case, it's PubSub IO, and then you do a bunch of transforms. And finally, you actually write that output to a sink. In this case, we are writing it to BigQuery. The good thing about Apache Beam is that it has connectors for pretty much most of the common components outside Google Cloud as well. So let's say if you're using Kafka, rather than PubSub IO, you just need to use Kafka IO. If you're using MQTT, we have MQTT IO. And the same works for other bounded sources as well. For example, if you need to read data from MongoDB and write to BigQuery, you can use MongoDB IO. So after Apache Beam was open sourced, the community has developed a lot of connectors and IOs on top of it. So it's like very user friendly, and you don't have to write like separate pipelines to ingest data from multiple sources. Okay, so let's talk about a use case. Let's talk about some of the most common use cases in Stream, in which we can basically use Apache Beam and Cloud Dataflow. Okay, so the first one is exactly once processing. Now, let's say we take the same mobile game example. You have players playing your mobile game. Events are getting ingested. Now, what you want to do is you basically want to aggregate the scores of each and every user at specific time ranges. And in that, what you want is you want to eliminate duplicates. Now, traditionally, the way people have been handling duplicates in a streaming pipeline is to basically run ETL or run a pipeline once the data for the entire day comes in, and then remove the duplicates. But with Apache Beam, you can actually remove the duplicates as your data comes in. So this is how you do it. So basically, in this case, let's say you have 3 events which get published, and they're published to PubSub, which is the messaging bus. But with PubSub, it guarantees at least once delivery. That means if let's say when I was trying to publish event to PubSub might even deliver that event twice. So how do I handle the duplicate, which is the 2 yellow events at the subscriber level? So let's take the example of the game event itself. So this is the sample data in the game event, which is basically an event ID, timestamp, user ID, level, and score. Now, the way we can handle duplicates is using a feature called as attributes. So attributes is basically when you actually generate an event, so you can actually generate a key value pair. So you can choose a unique column or a unique field and put that into attribute. Now, in this case, event ID is something which is unique. So every time somebody plays a game or a score gets submitted, a unique event ID gets generated. So we can use that event ID in the same pipeline, and we can actually use that to remove duplicates. So this is how we can remove duplicates. So basically, the thing which we need to do is to tell PubSub in Dataflow to use event ID as the attribute, and the moment we write that, it automatically deduplicates the messages using the event ID. So in this case, basically, even though there were 2 yellow events, but by just these 3 lines, it removes that extra yellow event. Now, as I said before, if you wouldn't have been doing this, you would be actually running a fat ETL or a fat pipeline job at the end of the day, which might take like multiple hours to remove the duplicates. And this is how you can do that in real time itself. Now, the second case is dealing with bad data. So in stream processing, bad data is very common. So let's say if you have an application and you have like 100k events per second or even more than that, there is a very high chance that bad data can be generated. So in this example, the same example, if you see, this event is basically a bad data. Can one of you explain why this is a bad data? Yeah, so basically there are many reasons. You can see that this is a JSON event and the end tag is missing, which is very, very common. Also, the event ID is not string here. We were expecting a string, right? So these are very common examples of bad data, right? Now, how do I handle a bad data without even compromising my pipeline? So when I'm running a streaming pipeline and I encounter a bad data, I wouldn't want to stop my pipeline. I would want to have my pipeline running as it is and handle the bad data separately without impacting the existing pipeline. So the way we handle that using the Apache Beam SDK is basically in the catch block, So whenever whenever you encounter a error or bad records, in the catch block, you can basically call a function, and that function will basically write the events which were malformed into a separate BigQuery table, and it will also send a trigger to PubSub, which will send you a notification. So without even breaking your existing pipeline, you can come to know about bad data, and you can also react to that bad data. And if you see in this, I'm also writing the failed messages to BigQuery, because I want somebody from my operations team to kind of look into and see what was the reason due to which that data failed. And by doing this, I'm not impacting my existing pipeline. And after I look into the data and find out the reason, I will have an option either to drop this data or maybe reprocess it and merge it with the existing table as well. The third thing is handling schema changes. Okay, so basically in stream processing, schema changes is very common because let's say you have an application that are like 20 products, and each product is being built by a separate engineering team. So the team who is handling the data ingestion, they are actually handling data ingestion from 20 different product teams, and each and every product team can add or remove an attribute in their event at any point of time without even informing the data engineering team or the team who is handling the data ingestion. But because the schema has changed or the schema got altered, you wouldn't want your pipeline to break. So how do you handle schema changes? So the way we handle schema changes is, okay, so let's take the same example. In this case, this was our previous event, and you can see that in the new event, there was a new field as partner device IP added by the application team. Now, when I try to insert this event into BigQuery in my same pipeline, this will fail because my BigQuery table, my sync table, only has, let's say, 5 columns, and this is a 6th column. So how do I mutate my BigQuery table even when the stream is getting processed, and then insert the failed events back to the same table? So the Beam SDK has a pretty decent integration with BigQuery when it comes to handling schema changes. So the way you can handle schema changes is you can basically have a separate method in your same pipeline, and that method would actually call a function which will go ahead and alter the BigQuery table in real time and add the new field. And then all the failed records in the first step will get automatically reprocessed and merged into the same table, right? Now imagine if you don't have this, then you would actually stop your pipeline and then probably go ahead and alter the table and then restart your pipeline. But if you do that, you might end up spending a lot of time in just making the schema change. But with the Apache Beam SDK, this is supported out of the box. So there is no impact in your existing pipeline. Yeah, so this is how you handle the dynamic schema mutation. So as the errors happen, you go ahead and mutate your table, and then the failed records, they get automatically inserted back to the same table which has the new schema now. Okay, the fourth use case is real-time denormalization. So basically, one of the very common use cases in stream processing is data enrichment. So let's say, if I take the same mobile game example and I have users playing that game, I would want to enrich the existing stream data by some additional information, which might be, let's say, by user location or user profile, or if I want to segment the user in real time using the same event, I would want to enrich that data. So how can we do data enrichment in real time in the same pipeline? So the way we do data enrichment is basically we store our reference data, or you can call it as dimensional data, in a separate storage or in a separate database. So in this case, we are using Cloud Bigtable because when you're doing a real-time enrichment, you wouldn't want to wait for seconds to get the data from the from the database. If let's say I'm using BigQuery instead of Bigtable, since BigQuery latency is like sub-second, my pipeline would have to wait every time I go and do a lookup in BigQuery. So that's why I'll go for Bigtable or Cloud Data Store or even a MySQL database as well. So as your data comes in, you can perform per record lookups into a separate data store. It might be Bigtable, data store, or even MySQL as well. And the output of the per record lookup you add with the existing stream data, and then you enrich your data and do aggregations on top of it. Now, basically Imre kind of covered what a Pardue means in the previous session, and basically when you do a per record lookup, you would basically make a connection to the other database, which is Bigtable or data store or even MySQL. Now, since in the way Cloud Dataflow works is it basically bundles your records, and that records are executed or processed at one worker. So basically the connections which are made, they are made at a worker level. So you're not making the connections for each and every record, right? And that is also handled automatically by the SDK itself. Okay, so this is what we were doing. So in the third step, which is the enrichment step, we basically made a connection to another database, which is Bigtable in this example, and then we did a per record lookup. After the per record lookup, we just close that connection. So if I try to visualize this, basically the same pipeline, I'm doing an enrichment from Bigtable, and that enriched result is getting written to BigQuery itself, right? So this is another common use case in which you can actually do stream analytics by enriching your data from an external source. Okay, the fifth use case is user behavior analysis. So basically, if you take the same game example, and I want to know how long a particular user spent playing the game. Now, if I use fixed windows, which is if I take, let's say, 1 hour time lab and then calculate the aggregation, there is a very heavy chance that the same mobile application or the same phone might be used by multiple people within the family. So let's say I start playing the game, I pass it over to my brother or somebody else, or even to my friend, right? And then if I am doing the computation at the end of 1 hour, the results might not be very promising because there might be multiple people who have used that particular game. So in that case, what I want to do is I want to do an aggregation for each and every session, right? And that session could be as small as possible. So basically you can do an aggregation every minute, every 2 minutes, or every 5 minutes as well. So if I have to aggregate the data based on session, the only change I need to do is I need to choose in this case, I choose the user ID, and as a key, and based on the key, I basically pull up all the records for that particular session. And in this way, I'll be able to achieve much more accurate results. And I'm doing this at every 5 minutes, rather than doing it like every 1 hour. So the same example, in this case, the only thing which I'm doing is that I use session-based windows, which is using the user ID, and then I was able to basically group the records based on the user ID and then write it to BigQuery. Now, we are using the same diagram, but each and every use case will end up creating a separate BigQuery table, which might be serving a particular analytical use case. Okay, so this was about Apache Beam SDK. What I also wanted to just introduce is BigQuery ML. Again, this has nothing to do with Apache Beam and Cloud Dataflow. So we announced BigQuery ML a month back in our annual Next conference, and the reason why I'm bringing BigQuery ML and explaining to you guys is that traditionally machine learning has been viewed mostly from a data science perspective, And generally people who don't have data science expertise, people think that they can't do data science. Like I'm a data engineer, I'm an analytical engineer, so I'm not a data science graduate. But now with BigQuery ML, I can do data science as well. So, the key features of BigQuery ML is that it's supported out of the box on BigQuery itself. It's pretty much SQL based, so you can basically create your models in BigQuery, you can train your models, and you can predict your models. And all of these you can do by just plain SQL. A few things that right now, the models which are supported on BigQuery ML is mostly regression based, which is linear regression, logistic regression. But if you just take example of these two models, pretty much most of the use cases are covered under regression. So if you have to do a regression, you don't have to write a machine learning model. You don't have to tell your data scientist to give a model just to do linear regression or even logistic regression. So yeah, these are the supported features as of today, but this is going to improve, and new things are going to get added in future as well. It's already in beta right now, so you can just go ahead and start building machine learning models on top of BigQuery. For more documentation, if you just search for BigQuery ML, there is enough documentation for you guys to get started on BigQML. Okay, so this is where BigQML stands, right? So we're not saying BigQuery ML is going to solve all data science problems in the world. So basically, BigQuery ML is targeted as SQL analyst or data analyst, right? So you have your data scientist, who continue to build their machine learning models, deep neural networks, TensorFlow, Keras, scikit-learn. And then you have the pre-baked machine learning APIs like AutoML, Vision API, Translate API. So BigQuery ML is kind of sitting in between both of them. Okay, that's all from my side. Before I close, we are having our Google Cloud Summit on 4th October. Many of you might be knowing about this. We did this last year as well, and we are expecting close to 4,000 plus people at our summit. It's like a one-day summit. There will be a keynote, and there will be around 20 technical sessions from customers, Googlers, and other industry experts. So if you just search for Google Cloud Summit Jakarta, you'll get the link, but the registration link is there. If you open this link today, we closed down the registrations because we maxed out the capacity, but feel free to walk in and attend the summit. There will be 3 separate tracks: infrastructure, data analytics, machine learning, and collaboration. So altogether, there will be around 20 sessions to attend. Yeah, so that's all from my side. Thank you.